telescope stared into the dark and found a ring of galaxies so wide it should not exist, 1.3 billion light-years across, bigger than the rules of physics allow. Tonight we travel out to that ring, to galaxies that grew up far too fast, to a wall of light stretching 10 billion light-years across the sky. Each one breaks a law the universe was built on. If the deep cosmos pulls at you, tap like and subscribe. We are about to break the universe. Begin. Every map of the universe you have ever seen starts with a quiet promise. Zoom out far enough, and everything smooths over. Picture the ocean from an airplane window. Up close, the water churns with waves and foam. From 6 miles up, it flattens into a sheet of blue. Cosmologists believe the universe works the same way. Up close, it looks lumpy, full of stars and galaxies and empty gaps. Step back far enough, and all of it should blur into one even, grey haze. Scientists call this the smoothness rule. It says that if you stand anywhere in space and look around, you should see roughly the same thing in every direction. The same number of galaxies, the same scatter of light, no giant clumps, no special address, no center of it all. This idea sounds almost boring. It is the most important rule in all of cosmology. Nearly every calculation about how the universe was born, how old it is, and how it will end leans on it. Pull that rule out, and the math behind reality starts to wobble. Here is the strange part. The rule only kicks in above a certain size. Below that size, lumps are allowed. Our galaxy is a lump. Our whole neighborhood of galaxies is a bigger lump. Scientists worked out the size where the lumpiness has to stop and the smoothness has to begin. That line sits at around 1 billion light-years. Anything wider than that should melt into the even haze. To feel how big that line is, try to walk it. Light is the fastest thing in the universe. It can cross our entire galaxy in a flash, on cosmic terms. Yet light needs a full billion years to cross one of these giant patches. The dinosaurs had not even appeared when that light set out. So the rule is simple. Nothing in the universe should be organized, arranged, or strung together across a gap bigger than that. Past that line, the cosmos is supposed to forget how to build. For almost 100 years, the rule held. Every survey of the sky seemed to agree. Galaxies clustered into groups, groups gathered into clouds, and then, right on schedule, the pattern dissolved into static. The promise kept itself. Then telescopes got sharper. Astronomers started mapping the sky deeper than anyone had before, charting millions of galaxies at distances that used to be invisible. They expected the same old answer: smoothness. Static, the familiar grey haze. Instead, shapes began to appear in the dark, long ones, curved ones, round ones. Patterns that stretched across the sky, far past the line where patterns were forbidden. At first, the scientists assumed they were seeing things. A trick of the eye, a run of bad luck in the data. Random dots can fall into fake shapes, the same way clouds sometimes look like faces, so they checked. They ran the numbers again. They measured the odds. The shapes refused to go away. To understand why a shape in the sky is so alarming, you first have to see how galaxies are normally arranged. They do not float alone, scattered at random like grains of sand. They hang on something, a hidden structure that runs through all of space, invisible, vast, and older than the stars. We are about to look at the skeleton of the universe. Imagine the largest spiderweb you can. Now stretch it across everything that exists. Galaxies do not drift through space like loose marbles in a jar. They line up. They gather along invisible threads that reach across unthinkable distances, meeting at glowing knots where thousands of galaxies pile together. Between the threads sit huge, dark, empty rooms. Scientists call this whole arrangement the cosmic web. If you could shrink the universe down and hold it in your hands, it would look a little like a sponge, or a human brain, with its folds and channels, or sea foam, full of bubbles pressed against bubbles. The solid parts hold the galaxies. The hollow parts hold almost nothing at all. The threads have a name, Scientists call them filaments, and they are the largest structures in nature. A single filament can stretch for hundreds of millions of light years, a river of galaxies flowing toward a city of galaxies at the far end. Our own Milky Way sits on the edge of one of these rivers, drifting slowly toward a giant cluster we may never reach. What holds the web together is the part you cannot see. Most of the universe is built from something invisible called dark matter. It gives off no light. It makes no sound. You could pass through a cloud of it and never feel a thing, yet its gravity is the glue. In the early universe, dark matter clumped first, laying down the threads. Then ordinary gas fell into those threads, lit up, and became the galaxies we can finally see. So the glowing web in our telescopes is only the decoration. The real frame underneath is dark, silent, and far heavier than everything that shines. This explains why a strange shape in the sky matters so much. Galaxies follow the web. The web was laid down by gravity in the first moments of the universe. And gravity works slowly. It needs time, an enormous amount of time, to pull matter into long strands and round knots. The bigger the structure, the longer it takes to build. Here is where the trouble starts. The universe has only existed for about 13 billion years. That sounds endless. For gravity, it is a tight deadline. There has only been enough time to weave the web up to a certain size. Past that size, the threads should simply run out, and the pattern should dissolve into a fine, even mist of galaxies sprinkled in every direction. That size limit is the same line from before, around 1 billion light years. Build a wall of galaxies longer than that, and you are asking gravity to do a job it has not had the years to finish. For decades, the web behaved. Astronomers mapped its threads and knots and empty rooms, and everything fit the deadline. Galaxies clustered, then thinned out, exactly on time. Then the deepest surveys began returning maps no one expected. The web seemed to keep going. Threads connected into longer threads, knots lined up into chains. Something out there had woven patterns far larger than the deadline should allow, as if the universe had cheated the clock. To chase those patterns into the deepest, oldest corners of space, astronomers needed a new kind of eye, a telescope that could see heat instead of light, peer through walls of cosmic dust, and stare so far away that it looked back into the past. That eye already exists. It is watching right now. On Christmas morning in 2021, humanity folded a telescope into a rocket and shot it toward the dark. It is called the James Webb Space Telescope, and it sits about 1 million miles from Earth, 4 times farther than the Moon, parked at a calm spot in space, where our planet never blocks the view. Its main mirror spans more than 21 feet across, wide enough that a tall person could lie down on it twice over with room to spare. The mirror wears a coat of real gold, thinner than a hair, polished to catch the faintest glow in existence. To fit inside the rocket, the whole thing folded up like a piece of origami, then unfolded itself perfectly once it reached space. No repairman waited out there. One jammed hinge, and the mission was finished. Older telescopes, including the famous Hubble, mostly see the same kind of light your eyes do. James Webb sees something else. It sees heat. It reads infrared light, the same invisible glow your warm body gives off in a dark room. The kind night vision goggles paint in ghostly green. This single choice changes everything. Infrared light slips straight through dust, and space is choked with it. Thick clouds of dust hide newborn stars and faraway galaxies from ordinary telescopes. To Hubble, a dust cloud can look like a brick wall. To James Webb, that same wall turns clear as window glass, and whatever hides behind it leaps into view. To catch a glow this faint, the telescope has to run colder than almost anything in nature. Its own warmth would blind it, the way a candle wrecks your night vision. So James Webb crouches behind a sunshield the size of a tennis court, 5 thin layers that block the heat of the Sunday. In its shadow, the instruments fall to hundreds of degrees below zero. The cold side of that telescope is one of the chilliest spots ever made by human hands. Engineers spent more than 20 years and $10 billion building it. They launched it knowing that hundreds of separate steps all had to work, alone, in the dark, with no one able to reach it. Every single one of them worked. Then the telescope opened its golden eye and began to drink in the oldest light around. Here is where space starts to bend your mind. When James Webb stares at something far away, it is staring at something long gone. The deeper it looks, the older the view becomes, until it reaches scenes from a time before the Earth, before the Sun, before almost anything you could name. The light landing on that mirror is ancient. Some of it has been traveling since the universe was only a few 100 million years old, a tiny sliver of its life. The galaxies in those images are not showing Webb what they look like today. They are showing it baby photos, snapped when the cosmos had barely begun. To understand how a telescope can photograph the past, you have to understand the one fact that makes all of astronomy possible. Light is fast. It is also, in its own way, slow, and that strange truth turns every telescope into a time machine. Look up at the sun, and you are looking 8 minutes into the past. That sounds impossible, yet it is the plain truth. Light is quick, the quickest thing there is, but it is not magic. It takes time to travel. Sunlight needs about 8 minutes to cross the gap from the sun to your eyes. If the sun blinked out right now, you would keep seeing it shine for 8 full minutes, basking in light from a star that was already gone. Every glance you take is a glance backward. The far wall of a room shows you light that left it a tiny fraction of a second ago. The moon at night is the moon as it looked just over a second in the past. The truth is, you have never seen anything exactly as it is. You only ever see how things were when their light set out. For nearby things, the delay is too small to notice. Stretch the distances out, and the delay becomes a window into history. The next star past our sun sits so far away that its light takes more than 4 years to reach us. So you never see that star as it is tonight. You see it as it was 4 years ago. Push out to other galaxies, and the numbers explode. The light from Andromeda, the nearest big galaxy to ours, left on its journey about 2.5 million years ago, back when our distant ancestors were learning to chip stone tools. The galaxy could have changed completely since then, and we would have no way to know yet. Now you can see why a powerful telescope is really a time machine pointed at the sky. The farther out it looks, the deeper into the past it digs. Distance and time become the same measurement. A galaxy 10 billion light-years away is also a galaxy 10 billion years back in history. This is the secret weapon of the James Webb Space Telescope. It was built to look so far that it reaches the universe's opening chapters. Astronomers wanted to catch the very first galaxies in the act of forming, to watch the lights of the cosmos flicker on for the first time. Think of the whole history of the universe squeezed into a single year. The Big Bang happens at midnight on the 1st of January. Earth does not even show up until late summer. All of human history fits into the final few seconds before the next new year. James Webb was made to see January, the first cold mornings of creation, when the first galaxies were still tiny smudges of new light. When the telescope reached those first chapters, scientists expected to find faint, small, simple galaxies, little seeds, soft sparks, barely holding themselves together. The standard story of the universe was clear about this. Big things take time. The early cosmos should have been a nursery, full of small and gentle beginnings. The light that came back told a different story. In the oldest, deepest images, where the universe should have been quiet and dim, the telescope found galaxies already blazing. Some looked too bright, some looked far too large. They sat in a moment when nothing that grown up was supposed to exist. Before we can understand why that broke the rules, we need to know how scientists pin an exact age onto a single point of light. The answer is hidden in its color. A galaxy is just a smudge of light in a photo. So how does anyone know it sits 13 billion years in the past and not 3 or 30? The answer is color. Hidden inside the light of every galaxy is a kind of barcode, and that barcode tells us how far the light has traveled. Start with something you already know. Picture an ambulance racing past you with its siren screaming. As it speeds toward you, the sound bunches up and the pitch climbs higher. As it races away, the sound stretches out and the pitch drops lower. The siren never changed. The motion stretched the sound waves on their way to your ears. Light behaves in a similar way. When something glows while moving away from us, its light waves get stretched out. Stretched light slides toward the red end of the rainbow. Scientists call this shift toward red exactly what you would guess: redshift. The faster something flees from us, the more its light reddens. Here is the twist that makes the whole universe a puzzle. Space itself is expanding. Every corner of the cosmos is slowly spreading apart, like dots drawn on a balloon as someone blows it up. The dots themselves stay put. The rubber between them grows. In the same way, distant galaxies ride along as the space between us and them stretches, carrying them outward. And here is the gift this gives astronomers. The light from a far galaxy spends billions of years crossing that stretching space. The whole time, its waves get pulled longer and redder. So the redder a galaxy looks, the longer its light has been traveling, and the farther back in time we are seeing it. Measure the exact shade of red, and you can read the distance like a number on a ruler. A faint, deeply reddened galaxy is far away in space and far away in time, a relic from when the universe was young. The deepest red glows in Webb's images come from galaxies whose light set out more than 13 billion years ago, when the cosmos had lived through only the first slice of its life. This is why infrared eyes matter so much. The oldest light has been stretched so far past red that it has left the rainbow entirely and turned into heat. Your eyes cannot see it. Hubble could barely reach it. James Webb was built to catch exactly this stretched, ancient, reddened glow, and to pin a precise age onto every smudge it finds. With this ruler in hand, scientists can do something remarkable. They can sort galaxies by age. They can line up the universe's whole family album, from the newborn galaxies of the deep past to the grown ones nearby. They can ask a sharp question: how big were galaxies supposed to be when the universe was still a baby? The standard story gave a confident answer. In those first few 100 million years, galaxies should have been small, faint, just getting started. The big, bright, heavy ones were supposed to come much later, after billions of years of slow growth. So when astronomers measured the deepest galaxies in Webb's very first images, they already knew what the numbers should say: small, faint, barely born. The numbers refused to cooperate, and the more pictures the telescope sent home, the worse the problem became. The first deep pictures came back, and the early universe was crowded. Astronomers had built careful predictions before James Webb ever launched. They knew roughly how many galaxies the young cosmos should hold, and how bright those galaxies should shine. The early universe was supposed to be a thin, quiet place. A few faint sparks here and there, scattered across a mostly empty dark. The images showed the opposite of quiet. Galaxies appeared everywhere, packed into the deep field in numbers no one had ordered. Where the models promised a handful of dim smudges, the telescope delivered crowds of them, bright and clear, reaching back to ages the early universe was never meant to fill. Each fuzzy blob in those photos is a galaxy made of billions of stars. The pictures held so many that scientists had to become detectives, studying each smudge for clues about how far away it sat and how heavy it had grown. Most of these objects are too distant to ever see in detail. A blurry red dot is often all the information there is, and from that single dot, a whole galaxy has to be measured. The detective work kept landing on the same uncomfortable answer. These galaxies were too far, which meant too old, which meant they should not have looked so finished. They were already bright, already busy, already loaded with stars, in a stretch of time when the universe had barely started building anything at all. To feel the trouble, think about a forest. You expect a young forest to be full of seedlings, thin little sprouts poking out of the soil. Now imagine walking into that young forest and finding towering, full-grown trees, hundreds of years old, standing in ground that was planted only last week. The trees should not have had the time to grow, yet there they stand. That is what the early universe looked like through Webb's eyes. Grown galaxies in a place too young to grow them. At first, the scientists stayed calm. New telescopes always need fine-tuning. When James Webb first switched on, its instruments were still being adjusted, and rough early measurements can fool you. Some of the strange galaxies, they figured, would shrink or shift once the calibration improved. So the team checked their work, sharpened their numbers, and waited for the problem to soften. The problem did not soften, it spread. Survey after survey turned up the same picture. The deep universe was richer, brighter, and busier than the standard story allowed. One large project after another scanned slices of the ancient sky, and each one came back crowded with light that should not have been there yet. This was more than a counting error. The number of galaxies in a region tells scientists how fast the universe built its structures. Too many bright galaxies, too early, means the cosmos assembled itself in a hurry, far faster than the slow and steady growth the models predicted. Speed like that points at something missing from our picture of how everything came to be. Still, a crowd of bright galaxies was only the warm-up. Brightness can be argued over. Counts can be debated. The real shock was waiting inside a single one of those red dots. The one a scientist almost dismissed before it rewrote what he thought was possible. He ran the numbers on that tiny smudge. Then he ran them again, certain he had made a mistake. An astronomer named Ivo Labe was scanning through Webb's earliest deep images when he stopped on a single red dot. It looked like nothing, a pinprick, the kind of faint speck a tired eye would skip right over. Out of curiosity, he fed it into the software that measures a galaxy's distance and weight, expecting an ordinary answer. Two numbers came back. The first was distance. The light from that dot had traveled about 13 billion years to reach the telescope, which placed the galaxy in the deep early universe, only a few 100 million years after the Big Bang. The second number was mass. That little speck held roughly 100 billion stars worth of material, about as many stars as our entire Milky Way carries today. He nearly spilled his coffee. By his own account, he stared at the screen and realized he was looking at something that was not supposed to be there. A galaxy that full, that heavy, that early, broke the rules of how fast the universe was allowed to build. In his words, the team had just discovered the impossible. Impossibly early, impossibly massive. To understand his shock, remember the timeline. Our Milky Way took billions of years and many generations of stars to grow into the giant it is now. It built itself slowly, gathering gas, forming stars, swallowing smaller galaxies, brick by brick, over most of cosmic history. The standard story says there is no shortcut. Galaxies that big simply need that much time. The red dot had skipped the wait. It had somehow grown a Milky Way's worth of stars, while the universe was still a toddler, in a sliver of time far too short for the slow building to finish. Picture stumbling onto a finished skyscraper standing in a field where the first shovel had only just hit the dirt. One strange galaxy might be a fluke, a bad measurement, a trick hiding in a single blurry image. Labe knew this better than anyone, so he did the careful thing. He kept looking through the rest of the deep field, half hoping the next galaxy would behave, settle down, and let the old story stand. What he found instead turned one impossible galaxy into a crisis. The careful work mattered because everything rode on it. If a single faint smudge could really hold as many stars as the Milky Way, this early in time, then the comfortable order of the universe was upside down. The story had always run in one direction: small things first, big things much later. Stars gather into little galaxies. Little galaxies crash together into bigger ones. And only after billions of patient years do the true giants appear. This red dot put a giant at the very start, in the opening act, where the script said the stage should still be nearly empty. and one giant in the wrong scene is strange. A whole cast of them would be something else entirely. So Labbe and his team kept combing the deep field, dot by dot, distance by distance, bracing for what the next smudge would say. They did not have to wait long. The very next morning, the early universe handed them five more giants, spread across the same patch of ancient sky, each one heavier than the early universe should have been able to build, together with the first red dot that made six. 6 heavyweight galaxies crowded into a moment when the cosmos was supposed to hold nothing but faint little sparks. Scientists gave them a name that fit the trouble they caused: the Universe Breakers. The nickname spread through the field within weeks, half as a joke and half as a warning, because every one of these galaxies seemed to chip at the foundation of modern cosmology. The numbers were staggering. Some of these early galaxies appeared to hold up to 100 times more mass in stars than scientists had ever thought possible for that age. 100 times is no rounding error. If your weather forecast was off by that much, a prediction of 1 inch of snow would bury your town under more than 8 feet. A gap that wide is a sign that something in the recipe is badly wrong. These giants showed up together, too, in the kind of place the early universe was meant to keep simple, and they looked mature, settled, and full. Picture flipping to the first page of a photo album, expecting a newborn, and finding a grown adult already staring back at you. To see why this rattled scientists so deeply, you have to look at the order they believed the universe followed. The rule was simple, and it felt safe. Start small, build slow. The first galaxies should have been tiny clumps, barely held together, sparking their very first stars. Over hundreds of millions of years, those clumps would gather more gas, light up more stars, and slowly fatten into the great spirals and giants we see around us now. The Universe Breakers shoved that timeline into reverse. They placed the heavyweights at the very beginning, in the opening minutes of the cosmic story, when the slow building had barely started. It was as if the universe had run its whole growth spurt in fast forward, packing billions of years of work into a few 100 million. For a while, scientists wondered if the early cosmos simply turned its gas into stars far more eagerly than anyone guessed. Maybe these galaxies were bending the rules rather than breaking them, forming stars at a furious, greedy pace the models never expected. Even that explanation ran into a wall. Building a galaxy takes more than gas and speed. It takes a hidden frame to build on, a scaffold of invisible material that has to be in place first. Without enough of that scaffold, the gas has nothing to gather around, and no amount of speed will help. And when scientists checked whether the early universe held enough of that invisible scaffold to raise these giants, the answer came back short, far short. The missing ingredient was the strangest substance in all of science. Nobody has ever seen it, touched it, or caught a single piece of it. Yet without it, the Universe Breakers should not exist at all. Every galaxy in the universe is built on a frame you cannot see. Scientists call that frame a halo, and it is made of dark matter, the invisible substance that outweighs every star, planet, and person combined. A halo is a giant ball of this dark material, and its gravity is what pulls ordinary gas inward. The gas falls in, piles up, heats up, and finally ignites into stars. No halo, no galaxy. The invisible frame always comes first, and the visible galaxy grows inside it. Think of the halo as the steel skeleton of a skyscraper. The shining glass and the offices are the galaxy. You cannot hang the glass in midair. You raise the steel first, then build everything else onto it. In the cosmos, the steel is dark matter, and it has to be standing before a single star can form. Here is the catch that makes the Universe Breakers so painful. In the standard story of the universe, these dark matter skeletons grow slowly, the same way galaxies do. Small halos form first. Over time, they pull together into larger ones. A truly giant halo, big enough to raise a galaxy with 100 billion stars, takes a long time to assemble. In the deep early universe, the moment where Webb found those giants, the math says only small halos should have existed, little frames, modest skeletons. nowhere near enough big ones to build the heavyweight galaxies sitting right there in the images. The scaffolding to make them simply had not been raised yet. To put it plainly, the trouble runs deeper than speed. Even with unlimited time, the early universe lacked the giant frames these galaxies needed. A galaxy can only turn so much gas into stars, and that limit is set by the size of its halo. Even if the early universe formed stars as fast as it possibly could, cramming in every scrap of gas a halo could hold, the biggest early halos still come up short. There is a ceiling, and several of the universe breakers seem to punch straight through it. So scientists faced a hard fork. One path says our count of dark matter is wrong, and the early universe held far more of these giant frames than the models predict. That would mean we misunderstand the most common kind of matter in existence. The other path says dark matter behaves in some new way we have not yet imagined, building its skeletons faster and earlier than anyone thought. Either path tears at the standard model of cosmology, the carefully tested story that explains how the universe grew from a smooth, hot beginning into the structured cosmos we live in now. That model has passed test after test for decades. It predicted the faint ripples in the leftover heat of the Big Bang. It got the recipe of the early universe right. To question it is to question our deepest map of reality. And yet a stubborn voice kept asking whether the universe breakers were truly breaking anything. Measuring a galaxy from a single faint smudge is hard, slippery work. A bright glow can fool you about mass. A trick of light can fool you about distance. Before anyone tore up the rulebook, they had to ask a simpler question. What if the breakers were never impossible at all, and the telescope had quietly led us astray? Before you break the universe, you check your equipment. That was the mood among many scientists once the first wave of panic settled. Extraordinary claims demand hard proof, and measuring a galaxy that sits 13 billion years away from a smudge a few pixels wide leaves plenty of room for honest mistakes. So researchers went hunting for the boring explanations, the ones that would let the standard story survive. They found several. The first was calibration. When James Webb first switched on, its instruments were still being tuned, and early measurements ran a little off. Once teams sharpened those settings, some of the alarming galaxies cooled down. A few that looked impossibly heavy turned out lighter once the numbers were corrected. The second escape hatch was distance. A galaxy's danger depends on its age, and its age depends on how far the light has traveled. Pin the distance wrong, and you place the galaxy in the wrong era entirely. When scientists studied the universe breakers more closely, at least one of them turned out to sit closer than first believed. In a later time, when a big galaxy was perfectly allowed, moved to its true address, it stopped being a problem. The third hatch was the sneakiest. Scientists usually assume a galaxy's glow comes from its stars, and they weigh the galaxy by how brightly it shines. But stars are not the only things that blaze in space. A feeding black hole can pour out enormous light as it shreds and swallows the gas around it. If some of a galaxy's glow comes from a gorging black hole at its heart, then the galaxy holds far fewer stars than its brightness suggests. It would weigh much less, and the impossible mass would melt away. Sure enough, a batch of the strangest early objects turned out to be exactly this. Astronomers began calling them the little red dots, and many of them seemed to shine because of bright, hungry black holes hiding inside small galaxies, rather than vast crowds of stars. Counted correctly, they stopped breaking anything. There is a fourth possibility, stranger and quieter. Perhaps the very first stars were built unlike the stars we know. The early universe may have favored giant, blazing stars, far heavier and brighter than the ordinary kind. A galaxy stuffed with these monster stars would shine fiercely while holding less total mass, fooling our scales into reading it as a heavyweight. Add all these fixes together, and the crisis softens. Many of the scariest galaxies have an ordinary answer waiting, and the standard model bends back into shape. For a while, it looked as if the universe breakers might quietly retire. The cosmos is not off the hook, though. After every correction, a stubborn handful of early galaxies remain. They are still too big, still too early, still sitting in a time they have no business filling, with no easy excuse left to explain them. Scientists are now staring at those survivors with fresh observations, trying to nail down whether they are truly as impossible as they appear. The verdict is not in, and while one fight raged over galaxies that were too big, too soon, a second mystery was quietly taking shape on a far larger scale. Single galaxies, even giant ones, a small change compared to what was coming, because the same telescope that found impossible galaxies was about to help map something so vast that it makes a whole galaxy look like a single grain of sand on a very long beach. Astronomers pointed James Webb at a single patch of sky and refused to look away. They scanned it again and again, layering image upon image, building the largest survey the telescope has ever made. The project is called Cosmos Webb, and its goal was bigger than any one galaxy. The team wanted to map the cosmic web itself, the giant scaffolding of filaments and voids that threads through all of space. The result is the clearest map ever made of that web. It reaches across nearly 14 billion years of cosmic history, tracing the network of galaxies back to a time when the universe was only about 1 billion years old, still in its early childhood. In the map, bright regions glow with dense chains and clusters of galaxies. Dark regions mark the vast, empty rooms between them. For the first time, scientists could see the skeleton of the young universe laid out in real detail. To gather it, the telescope collected light from a staggering number of galaxies, far more than any ground-based telescope had ever caught in that same stretch of sky. Where earlier surveys saw a sparse handful, Webb pulled in crowds, 10 times as many in some patches, each one a fresh dot on the map. More dots mean a sharper picture, and a sharper picture means a fairer test of the smoothness rule. Remember what that rule demands. Zoom out far enough, and the universe should even out. The web can be lumpy on small scales, full of clusters and gaps, but past a certain size, the lumps must blur into a smooth, fair scatter, the same in every direction. A clean map of the cosmic web is the perfect way to check whether the universe truly behaves itself at the largest scales. So scientists spread the map out and started measuring. They traced the filaments, they mapped the voids, they followed how the web changed as the universe aged, watching galaxies gather along the threads over billions of years, drawn together by the pull of unseen dark matter beneath. Much of it fit the expected story. The web grew the way the models predicted, thickening over time as gravity slowly pulled matter into place. In that sense, the deep map was a triumph, a confirmation that our basic picture of how structure forms holds up across most of cosmic history. A map this deep does more than confirm, though. It also reveals the oddities, the places where the web seems to stretch farther or clump harder than the deadline of cosmic time should allow. The bigger and clearer the map, the easier it becomes to spot a pattern that has no business being there. A faint shape that, on a smaller map, would have hidden inside the noise. And the universe, it turns out, is full of shapes. The deeper telescopes look, the more the sky fills with structures that strain against the smoothness rule. Walls, arcs, rings, chains of galaxies running on and on past the line where the pattern was supposed to stop. To understand how shocking these giants are, you first have to grasp the thing that surrounds them, the emptiness, because the cosmic web is mostly whole, enormous, yawning, almost perfectly empty regions that take up most of the room in the universe. And the size of a single one of those empty rooms is hard for any human mind to hold. Most of the universe is empty in a way that breaks the imagination. When you picture space, you might think of stars sprinkled fairly evenly across the dark. The real arrangement looks more like a foam of bubbles. The galaxies cling to the thin walls and edges of the bubbles. The insides of the bubbles hold almost nothing at all. Scientists call these empty insides voids, and they are the largest empty spaces in nature. A typical void can stretch tens of millions of light years across, and some run far larger. To cross one, light has to travel through dark, vacant space for millions upon millions of years without passing a single bright galaxy. If you were somehow dropped into the middle of a large void, the sky around you would look almost totally black. The nearest galaxies would be so far away that even they would barely register. You could spend a lifetime staring out and see hardly anything shine. Try to picture the scale a different way. Imagine the entire Milky Way, with its hundreds of billions of stars, shrunk down to the size of a single grain of sand. On that scale, a cosmic void would still be a dark room the size of a large house, with only a few grains scattered around its distant walls and nothing whatsoever in the middle. The emptiness wins by a landslide. Voids are busy places. In their own slow way, they are growing. As the universe expands, the empty regions swell, and their gentle outward push helps shove the galaxy filaments closer together. The voids inflate like rising bubbles in bread dough, pressing the dough into thin walls between them. Over billions of years, this is part of how the cosmic web sharpens its shape, with empty bubbles squeezing the bright threads ever tighter. There is a humbling possibility hiding in all this emptiness. Some scientists think our own galaxy may sit inside one of these underdense regions, near the edge of a giant void larger than most. If that idea holds up, it could even tug at some of the biggest puzzles in cosmology, changing how fast the universe looks like it is expanding from where we stand. We might be living in one of the quieter, emptier neighborhoods of the cosmos and not have fully realized it. Voids matter for another reason, and it loops straight back to the smoothness rule. The whole pattern of bright walls wrapped around dark bubbles is allowed, expected, even required, as long as it stays below a certain size. Bubbles a few 100 million light-years across fit the rule. The universe is permitted to be foamy at that scale, and our maps agree. The danger appears when the foam organizes itself too far, when the walls of galaxies link up into a single structure that runs on past the limit, curving and stretching across 1 billion light-years or more. That is where the foam stops being ordinary froth and starts looking like a deliberate shape, something built on a scale the cosmos should not be able to manage. And the first of these forbidden giants that astronomers ever pinned down was a wall, a vast sheet of galaxies so long that, when its true size was measured, it cracked open a debate that has never fully closed. It already pushed against the limit, and it was only the smallest of the giants still to come. In 2003, astronomers mapping the sky stumbled onto a wall. They were working with the Sloan Digital Sky Survey, a huge project that measured the positions of hundreds of thousands of galaxies and built a three-dimensional map of a slice of the universe. As the map filled in, a shape emerged from the dots, a vast sheet of galaxies, packed together into a single sprawling structure, far longer than anything most scientists expected to find. It became known as the Sloan Great Wall. End to end, it stretches more than 1 billion light-years, with some measurements pushing it closer to 1.5 billion. It is a curtain of galaxy clusters and groups hung across the cosmos, made of many thousands of galaxies, all bound loosely into one enormous formation. The numbers are hard to feel, so try this. If you could shrink that wall down until our entire Milky Way was the size of a dinner plate, the Sloan Great Wall would still stretch for thousands of miles, a ribbon of galaxies long enough to run clear across a continent. It is one of the largest things humans have ever charted in the sky. When it was announced, the Sloan Great Wall became a quiet headache for cosmology. Remember the smoothness rule and its size limit, the line that sits around 1 billion light-years. The wall brushed right up against that line, and by some measurements, leaned over it. A structure that big was supposed to be rare, to the point of nearly impossible, the kind of thing the universe should produce maybe once, if at all, in all the space we can see. For a while, scientists could make peace with it. Walls like this are loose, stringy things, more like a crowd gathering than a solid object. Where exactly a wall starts and stops is partly a matter of judgment, and careful counting could sometimes shave the giant down to a more comfortable size. The Sloane Great Wall sat right at the edge of what the rules allowed, close enough that the rules could still, just barely, hold their ground. It also fit a familiar shape. Walls and sheets are a natural part of the cosmic web. The web is built from filaments and the flat sheets where filaments meet. So finding a big sheet of galaxies, while surprising in its size, did not demand any brand new physics. It stretched the rules. It had not yet shattered them. Still, the Sloane Great Wall changed the mood. It taught astronomers to take the giant seriously, to keep watching the edge of the size limit, to wonder how many more enormous structures were hiding in deeper, unmapped slices of the sky. If one wall could grow this close to the forbidden line, what else was out there, waiting in the dark beyond the reach of the early maps? The wall raised a sharper question too. Where exactly is the line? Everyone kept talking about a size limit, a length past which structures should not exist. But where does that number come from? And how certain is it? The answer is no guess and no hunch. It is a hard prediction baked into the standard model of the universe, a specific distance the cosmos drew for itself in the very beginning. And once you know exactly where that line sits, the structures that cross it stop looking merely large. They start looking impossible. Scientists did not invent the size limit to be annoying. The universe set it. The standard model of cosmology, the tested story of how everything grew from the Big Bang, makes a clear prediction. Matter can clump into structures, but only up to a certain size. Past that size, the clumping has to stop, and the universe must smooth out into an even spread of galaxies, the same in every direction. Scientists worked out where that line falls. The number lands at around 1 billion light-years, and many careful estimates push it to about 1.2 billion. That is the theoretical ceiling. Below it, walls and filaments and clusters are all allowed. Above it, structure is supposed to be forbidden, dissolved into the smooth cosmic haze. Why this exact size? The answer reaches back to the birth of the universe. In the first instant after the Big Bang, the cosmos was a hot, dense soup, almost perfectly even, with the faintest unevenness running through it. Tiny ripples, regions a hair denser than their surroundings. Those ripples were the seeds of everything. The denser spots, pulled in more matter, grew heavier, and slowly became the galaxies and clusters and walls we see today. Here is the key. Those original ripples had a limited reach. They could only set up clumps so large, and no larger. Combine that built-in scale with the age of the universe, and the amount of time gravity has had to do its slow work, and you get a firm ceiling on how big any structure can grow. Around 1 billion light-years, and not beyond. The number falls out of the math, the same math that correctly predicts so much else about the cosmos. To feel how huge that ceiling already is, line it up against things you know. Light could cross our entire galaxy in a tiny fraction of this distance. The gap to our nearest big neighbor galaxy is barely a rounding error next to it. Even the Sloane Great Wall, that continent-sized curtain of galaxies, only just reaches the line. The ceiling is so high that almost nothing in the universe should ever touch it. This is what makes the smoothness rule feel safe. The size limit sits far above any ordinary structure. You could map the sky for a lifetime and expect to find, at most, one or two things that even come close. The universe was supposed to keep its giants rare and keep them under the line. So scientists had a clean test in front of them. Find a structure that clearly crosses the limit, confirm it is real, and you have caught the universe breaking its own deepest rule. You have shown that the smoothness it promised does not actually hold, and that the standard model, for all its triumphs, is missing something fundamental. For years, nothing crossed the line cleanly. The Sloane Great Wall flirted with it. Other large structures came close, then shrank under careful counting. The limit held, bruised but standing. To break it for real, someone would need a new way to see, a method that could reveal structures hidden far beyond the reach of ordinary galaxy maps. Out in the deep universe where the old surveys went blind, a young scientist was about to find exactly that method, using the brightest beacons in the entire cosmos as her flashlights. The brightest objects in the universe are not stars. They are the engines at the hearts of distant galaxies, called quasars. A quasar forms when a giant black hole at the center of a galaxy feeds on gas. As the gas spirals in, it heats up and blazes with the light of many trillions of stars, shining from clear across the universe. Quasars are so bright that we can spot them from billions of light years away, tiny pinpricks that outshine the entire galaxies around them. A young scientist named Alexia Lopez had an idea about how to use them. She realized that a distant quasar works like a flashlight aimed straight at Earth. Its light travels for billions of years to reach us, and along the way, it passes through everything that lies between: clouds of gas, galaxies, the thin material draped along the cosmic web. Most of that stuff is far too faint to see on its own. But when the bright quasar light shines through it, the material leaves a mark. Here is how the mark works. When quasar light passes through a cloud of gas, certain atoms in that cloud drink up specific colors of the light. Magnesium does this especially well. So when the quasar's light finally reaches us, it arrives with tiny gaps punched into it, dark slots where the magnesium swallowed its share. Each gap is a fingerprint, proof that a particular cloud of matter sits somewhere along that beam. By reading these fingerprints in the light of thousands of quasars, Lopez could map matter that no telescope could photograph directly. She was seeing the shadows that galaxies cast in the beams of distant flashlights, and from those shadows, she could rebuild the hidden structure of the deep universe. It is a little like mapping a dark forest by shining lasers through it from far away. You never see the trees. You only see which lasers get partly blocked and where. Trace enough blocked beams, and the outline of the forest appears out of the darkness. Lopez pulled her quasar light from the Sloan Digital Sky Survey, the same vast project that once revealed the Great Wall. Inside that ocean of data sat the fingerprints of countless gas clouds, scattered across the deep sky, waiting for someone to connect them. She began plotting where all those magnesium shadows fell, looking for patterns in the spread, expecting the usual fair scatter the smoothness rule promised. For a while, the dots looked random, just an even sprinkle of matter across the dark. Then, in one region of the sky, far out, where the light had traveled billions of years to reach her, the shadows started to line up. They traced a clean, sweeping curve, as if the matter out there had been arranged along the edge of some enormous, invisible shape. She measured the curve, then she measured it again, certain she had made an error, because the shape it traced was far too large to be allowed. The structure hiding in those quasar shadows stretched across billions of light years, a curve of galaxies on a scale the universe was never supposed to build. It was the first of two giants she would find in that very same patch of sky, and the first one already bent the rules past breaking. The shape Alexia Lopez found was a curve of galaxies, and it was gigantic. She named it the Giant Arc. It is a sweeping crescent of galaxy clusters and the gas around them, traced out by the magnesium shadows in the quasar light. End to end, the giant arc stretches about 3 1/3 billion light-years across the sky. Set against the size limit of roughly 1 billion light-years, this single structure runs nearly 3 times too long. Let that size settle for a moment. The smoothness rule says the universe should almost never produce anything that even touches the limit. The giant arc blows clean past it, sweeping across a span so wide that light itself would need billions of years just to travel from one tip of the arc to the other. A structure like this was supposed to be impossible, the kind of thing the standard model flatly forbids. The arc sits far out in the deep universe, in light that traveled for billions of years to reach us. So we are seeing it as it was long ago, when the universe was younger. That only deepens the trouble. There was even less time back then for gravity to have woven something so vast. The arc should not have had the years to form, and yet there it hangs, a curve of galaxies arranged with almost deliberate grace. When Lopez first presented the giant arc, the natural response from other scientists was doubt. The human brain is a pattern machine. It finds shapes in clouds, faces in wallpaper, animals in the stars. Maybe the arc was a trick of the mind, a few scattered dots that happened to fall into a pleasing curve. It would not be the first time a grand cosmic structure dissolved under a hard second look, so the doubt was put to the test. Scientists ran the arc through careful statistical checks, the kind of math that asks a blunt question. What are the odds that random, evenly scattered matter would line up into a curve this clean, this large, by pure chance? The answer came back small, very small. The giant arc looked real, and its size looked genuine, far too orderly to wave away as a fluke of the eye. That left cosmologists in an uncomfortable spot. They had a structure, apparently real, that crossed their deepest size limit by a wide margin. One such giant, all by itself, was already a serious challenge to the smoothness rule. It suggested the universe could organize matter on scales the standard models swore were off-limits. Scientists comforted themselves with one thought. Perhaps the giant arc was a freak, a single, once-in-a-universe oddity, the rare exception that slips through even a good rule. You might tolerate one impossible structure if it stands alone, a strange outlier in an otherwise smooth cosmos. Everyone could live with a single cracked tile in the floor. Then Lopez kept looking at that same patch of sky, the same deep region where the giant arc hung. She searched the quasar shadows for more, half expecting the rest of the area to behave, to settle back into the smooth scatter the rule demanded. Instead, a second shape began to surface from the data. A different one, a curve no longer, but something that should have been even more impossible. Something round, a near-perfect ring, sitting right beside the giant she had already found. Near the handle of the Big Dipper, a circle of galaxies hangs in the sky that should not be there. Alexia Lopez found it in the same deep region as the giant arc, traced once again through the shadows in distant quasar light. She called it the Big Ring. It is a vast loop of galaxies and galaxy clusters, arranged into a near-perfect circle, sitting billions of light-years away in the deep universe. The size is staggering. The Big Ring measures about 1.3 billion light-years across. Run a tape measure around its full edge, and the circle's circumference stretches close to 4 billion light-years. If your eyes could somehow see it glowing in the night sky, the ring would appear about 15 times wider than the full moon. A colossal hoop of galaxies painted across the dark. Both of its numbers cross the forbidden line. The diameter alone beats the size limit of roughly 1 billion light-years. The circumference dwarfs it. By every measure, the Big Ring is another structure the universe was not supposed to be able to build, and it sits right next to the first one, in the same slice of sky, at the same distance, in the same era of cosmic time. So now there were two ultra-large structures, each far past the limit, found by the same scientist in the same deep patch of the universe. One a sweeping arc, one a near-perfect ring. The comfortable idea that the giant arc was a lonely freak collapsed the moment the Big Ring appeared beside it. Finding one impossible giant is bad luck. Finding two, side by side, starts to look like a message. Lopez put the problem plainly. Neither of these structures is easy to explain in our current understanding of the universe. Their enormous sizes, their distinct shapes, and the strange fact that they are neighbors all seem to be telling us something important. The question is what? The shape of the ring made it even harder to explain. Scientists tried to match it to a known kind of cosmic structure, the giant spherical shells of galaxies that ripple out from the early universe and freeze into the sky. The Big Ring refused to fit. Its size was wrong for that explanation, and its shape was wrong too. Whatever drew this circle in the deep sky, it was none of the patterns scientists already knew how to make. Of course, a single ring could still be a trick of the eye, the same way the arc might have been. The human mind loves to find circles, so scientists checked the odds once more. asking whether random scattered matter could fake a loop this clean and this large. A physicist at one university summed up the result bluntly. The chance of the Big Ring being a fluke, he said, was vanishingly small. A real ring, then, a real arc. Two forbidden giants, parked side by side, both breaking the deepest rule in cosmology, both daring scientists to explain how the universe could possibly have made them. And the strangeness was only beginning, because when Lopez studied the Big Ring more closely, trying to pin down its true shape in 3 dimensions, she discovered that its real form was far stranger than the flat, simple circle everyone had first imagined. What the ring was actually doing in space turned out to be far harder to believe. Everyone pictured the Big Ring as a flat hoop of galaxies, a giant circle drawn on the dark sky like a coin seen straight on. Alexia Lopez kept studying it. She wanted to know the ring's true shape, the way it actually sits in 3 dimensions out in deep space. A circle in a photograph can hide its real form. Hold a coin face on, and you see a perfect circle. Tilt it, and the circle flattens into an oval. Lopez wanted to know what the Big Ring would look like if she could fly around it and view it from every side. The answer surprised even her. The Big Ring is a coil, a corkscrew, something closer to a loosely wound spring than a simple flat circle. We see it as a clean ring only because one end of that coil happens to point almost straight at Earth. We are staring down the barrel of a cosmic spring, and from our seat, the spiral collapses into a circle. Think of a spiral notebook's wire binding. Look at it from the side, and you see a row of loops. Look straight down the length of the wire, and all those loops stack into what looks like one round hole. That is roughly what the Big Ring is doing, a twisting, 3-dimensional shape that only pretends to be a flat ring because of the angle we happen to view it from. This deepened the mystery. A flat ring is already hard to explain. A giant corkscrew of galaxies, 1.3 billion light-years across, coiled in the deep universe, is a shape that fits almost nothing in our books. Gravity does not naturally wind galaxies into springs on this scale. Nothing in the standard story of how matter clumps together predicts a coil this enormous. And there is a quiet, uncomfortable detail buried in all this. The ring appears round to us because it points our way. If it pointed in almost any other direction, we would see a tilted oval or an edge-on streak, and we might never have noticed it as a special shape at all. So either we got astonishingly lucky to catch a giant coil aimed right at us, or there are many more of these structures out there, scattered across the sky at every angle, and we only ever spot the rare few that happen to face us. Both options unsettle scientists. Pure luck on this scale feels suspicious. A cosmos secretly full of giant coils and rings, most of them hidden by their angle, would mean the universe is far lumpier and more structured than anyone believed. Lopez had now found 2 impossible giants in the same patch of deep sky. One a sweeping arc, one a coiled ring posing as a circle, both far past the size the universe is supposed to allow. Both sitting in roughly the same direction, at roughly the same distance. That last detail turned out to matter more than anything, because when scientists checked exactly where these 2 giants sat in space, they realized the arc and the ring shared far more than a patch of sky. They were neighbors, close ones, hanging at the same depth in the universe, in the same slice of cosmic time, almost side by side. And the odds of that happening by chance were about to make the whole puzzle far worse. Out of the entire sky, the giant arc and the Big Ring sit almost on top of each other. When scientists measured exactly where each one lay, the numbers lined up in a way that made them uneasy. Both structures sit at the same distance from Earth, their light having traveled for billions of years to reach us. So we see them in the same era, the same slice of cosmic history. And on the sky, they sit only about 12 degrees apart, close enough that you could cover the gap between them with your fist held up at arm's length toward the stars. To feel how strange this is, remember how rare these giants are supposed to be. The smoothness rule says a structure bigger than the size limit should be nearly impossible. In all the space we can observe, you might expect to find one, if you are lucky. Finding even a single giant arc was already a shock to the system. Now imagine reaching into a bag holding every patch of sky in the universe, drawing out one rare giant, and then, on your very next draw from that same small corner, pulling out a second giant just as forbidden. The chance of two ultra-large structures landing in the same neighborhood, at the same distance, in the same moment of cosmic time, is tiny. That begins to look like a clue. Lopez said as much herself. The two structures, with their huge sizes, their distinct shapes, and their strange closeness, seem to be telling us something important about the universe. Whatever force or quirk built one of them may well have built the other. They feel connected, like two waves from the same hidden splash. Picture two enormous crop circles appearing overnight in neighboring fields. One circle might be a hoax or a freak of the wind. Two giant, intricate patterns side by side, made at the same time, point to a single cause behind both. The pattern stops looking accidental. It starts looking made. So scientists now had a doubled mystery. Two record-breaking structures, parked as neighbors, in a universe that should struggle to make even one. The smoothness rule was supposed to keep the largest scales of the cosmos bland, and even the same in every direction. Instead, one small region of the deep sky held two of the most organized, oversized structures ever found. This is the part that keeps cosmologists awake. A single oddity can be brushed aside as bad luck or a measuring slip. A matched pair, sitting together, resists every easy excuse. It hints that the universe has a way of building giant, ordered shapes that our theories simply do not capture, and that this corner of the sky caught it in the act. And the more scientists stared at the arc and the ring together, the more a wild thought took shape. What if these two giants are pieces of one single structure, far larger than either one alone? If that idea holds, the true shape hiding in that corner of the sky would be bigger than anything our rules were built to survive. What if the giant arc and the big ring are two halves of the same thing? It is only an idea for now, a possibility scientists are weighing rather than a settled fact. But it is a serious one, and it follows naturally from everything we have seen. Two enormous structures, at the same distance, in the same era, 12 degrees apart, both far past the size limit. The simplest way to explain a matched pair is often a shared origin. Maybe they form a single giant, one vast formation so large that we only catch glimpses of its edges, like seeing two distant peaks of one mountain range hidden in fog. Try to grasp the scale of that combined structure. The giant arc alone runs more than 3 billion light-years. The big ring spans over 1 billion. Knit them into one connected formation, and you are talking about a single arrangement of galaxies reaching across a stretch of the universe so wide that the words start to lose their grip. Light, the fastest thing in existence, would need billions of years just to travel across it. To picture how absurd that is, think about how much room it would take up. The largest structure, the smoothness rule comfortably allows, spans barely more than 1% of the visible universe. The giant arc and big ring, joined into one body, would sprawl across several times that, a single formation eating up a real, noticeable slice of all the space we can observe. The rules call for small, the sky keeps handing us enormous. Each time scientists find a bigger version of these structures, the pressure on the smoothness rule climbs. One oversized ring is a puzzle. A matched pair is a warning. A single connected giant, stretching across a huge fraction of the visible universe, would be something close to proof that the rule is broken, that the cosmos can organize matter on scales it was never supposed to reach. For now, the connection stays uncertain. Scientists need more data, more quasar flashlights, more careful mapping to know whether the arc and ring truly join into one body, or simply sit near each other by some strange chance. The honest answer is that we do not yet know. The mystery is wide open, and that uncertainty is its own kind of thrill. What is clear is the direction everything points. Deeper surveys keep finding structure where there should be smoothness, bigger shapes, stranger arrangements, patterns that stretch past every line scientists draw. The universe, looked at closely enough, seems stubbornly, impossibly lumpy at the very largest scales. And every one of these giants, the arc, the ring, the walls before them, leans on the same crack in our understanding. They all break a single rule, the deepest assumption in all of cosmology, the quiet promise that the universe is the same everywhere you look. Scientists gave that promise a formal name long ago. They built nearly the entire science of the cosmos on top of it. Almost every number we have for the age of the universe, its size, its contents, and its fate rests on this one idea holding true. It is time to put that idea under the microscope. Because if the rings and arcs are real, this cornerstone of modern cosmology may be cracking beneath our feet. The rule has a name. Scientists call it the cosmological principle, and almost everything we believe about the universe stands on top of it. The principle makes two promises. The first is that the universe looks the same in every direction. Turn to face one part of the sky, then spin around and face the opposite part, and you should see roughly the same scatter of galaxies either way. No special direction, no grand cosmic arrow pointing toward something. Scientists call this sameness in all directions isotropy. The second promise is that the universe looks the same from every place. Stand in our galaxy, or in a galaxy a billion light years away, and the view of the wider cosmos should be roughly identical. No special spot, no center, no edge, no privileged address. Scientists call this sameness everywhere homogeneity. Put the two together and you get a humble, almost beautiful idea. We are nowhere special, and no direction is special, and on the largest scales the universe is a smooth, even, democratic place. Both promises only kick in above that size limit, the line near 1 billion light years. Below it, lumps and clusters and walls are fine. Above it, the lumpiness has to fade into smoothness. Why would scientists build everything on an assumption like this? Partly out of humility. History keeps teaching us that we hold no special place. Earth circles the sun, rather than sitting at the center of things. The sun rides far out in the suburbs of the galaxy. Our galaxy is one of countless others. Assuming we are nowhere special is the safe, modest bet, and it has been right every time before. There is a more practical reason too. The cosmological principle is what makes the universe solvable. If the cosmos is the same everywhere and in every direction, then the math becomes manageable, and scientists can write clean equations for how it expands, how old it is, and how it will end. Take that evenness away, and the equations turn into a nightmare. Almost every headline number you have ever heard about the universe quietly assumes this rule is true. So consider the stakes. Our best estimate of the universe's age, around 13.5 billion years, leans on it. Our map of what the universe is made of leans on it. Our entire story of how everything will end leans on it. The cosmological principle is the floor the whole house is built on. Now picture giant rings and arcs and walls, real structures, stretching far past the size where smoothness was supposed to take over. Each one is a crack in that floor. Each one whispers that maybe the universe is not so even after all. Maybe there is structure on scales we swore were forbidden. Maybe, in some direction or some place, the cosmos really is different, lumpier, more organized than the rule allows. If that is true, the floor shifts, and everything built on it wobbles, cracking, slowly, in ways scientists are only beginning to measure. Faced with cracks like these, researchers do what good scientists always do. Before tearing down the whole house, they look for an ordinary explanation, a boring cause. Some known, gentle process that could fake a giant ring without breaking any rules at all. And for the big ring, they had one candidate in mind. A ghostly echo from the dawn of the universe, frozen into the sky. The early universe was loud. In its first few 100,000 years, the cosmos was a blazing fog of hot gas far too dense and bright for light to travel freely. In that fog, real sound waves rang out, pressure waves rolling through the hot soup like the boom of a struck drum spreading through air. These were the literal sounds of the newborn universe, ripples of pressure expanding outward from every dense spot. Then the universe cooled. After a few 100,000 years, the fog thinned, the gas calmed, and light was suddenly free to fly. At that exact moment, the sound waves froze. The pressure ripples stopped spreading and locked into place, leaving behind faint shells of slightly denser gas, each one a ring of pressure caught in the act of expanding. Over billions of years, galaxies grew thickest along those frozen shells. Scientists have a name for these fossil sound waves. They call them baryon acoustic oscillations, and they are real, confirmed, and woven all through the sky. Every shell is a giant sphere of galaxies, and crucially, they all come out to nearly the same size. Astronomers use them as a kind of cosmic measuring stick, a known length stamped across the universe, because every one of these frozen sound shells spans close to the same enormous distance. So when the Big Ring appeared, this was the first explanation scientists reached for, a ring of galaxies, born from a frozen sound wave from the dawn of time. It would be strange, yet it would be allowed. No broken rules. Just an old echo caught at the right angle to look like a perfect circle. The idea fell apart under two tests. The first was size. Those frozen sound shells all share one fixed width, that reliable cosmic measuring stick. The Big Ring came out the wrong size, too large to match the known length of the shells. A measuring stick that suddenly changes length is no measuring stick at all. The second test was shape, and it was worse. The frozen sound waves form spheres, full, round bubbles of galaxies. Seen from Earth, a sphere should look like a filled-in disk, brighter around its edge but present all the way across. The Big Ring is a true ring, and behind it sits the coil scientists later uncovered, a wound spring of galaxies. A bubble cannot fake a coil. The geometry simply refuses to match. So the gentle, ordinary explanation failed. The Big Ring is something else, a shape that does not fit the catalogue the early universe is known to produce. This is the moment the mystery turns serious. With the easy answer gone, scientists were left holding a giant structure that breaks the size limit, twists into a shape gravity should not make, and sits beside an equally impossible arc, the boring escape route closed. What remains is a hard question with no comfortable answer. How does a universe that is supposed to grow smooth and even at the largest scales keep building enormous, ordered, oversized shapes? Part of the trouble runs deeper than size or shape. It comes down to time. Because even if the universe wanted to build a structure this big, the clock says it never had the chance. There is a speed limit built into reality, and it is the speed of light. Nothing outruns it. Light is the fastest thing there is, and every other influence in the universe, including the pull of gravity, travels at that speed or slower. This simple fact carries a huge consequence. For two places to affect each other, to coordinate, to pull together into one shape, there has to have been enough time for a signal to cross the distance between them. If light has not had time to make the trip, then as far as physics is concerned, those two places have never met. Now apply that to a structure billions of light years wide. For galaxies on opposite ends of the Big Ring to arrange themselves into one connected coil, gravity would have to coordinate across the whole span. That coordination cannot travel faster than light. So crossing the structure, even at the universe's top speed, takes billions of years. Here is the problem. The universe itself is only about 13.5 billion years old. For a structure stretching across 1 billion light years or more, there has barely been enough time for one end to feel the other, let alone for gravity to slowly gather scattered galaxies into a clean, ordered ring. The clock runs out before the building can finish. Think of it like a stadium crowd doing the wave. For the wave to roll smoothly around the whole stadium, each person has to see their neighbor stand and respond in turn. That takes time to travel around the ring. Now imagine a stadium so vast that even moving at full speed, the wave could not make it even partway around before the game ended. You would never see a complete, coordinated wave. There simply would not be time. The two sides of the stadium would never learn what the other was doing. The big ring is that impossible stadium wave. It is a coordinated, ordered shape on a scale so large that the universe has not lived long enough to build it the normal way. Gravity, bound by the speed of light, could not have reached across the whole structure to organize it. And yet the structure is there, clean and curved and coiled, as if it formed in defiance of the clock. This is why scientists keep using the word impossible, and they do not use it lightly. These giants break more than a size guideline. They seem to break the basic bookkeeping of cause and effect, the rule that says influence takes time to travel, and the universe has only had so much time to spend, so the structures force a hard choice. Maybe these giants skipped the slow build entirely. Maybe they were stamped into the universe at the very beginning, born already huge in the first flicker after the Big Bang, before anything had to travel anywhere. Or maybe our understanding of time, distance, and the early universe is missing a piece we have not yet found. Either way, the rings and arcs are only part of the story. They are the most beautiful of the giants, and far from the largest. Out in the deep sky sit even bigger structures, walls of galaxies on scales that make the big ring look almost modest, and one of them was hiding behind our own galaxy the whole time. Our own galaxy has been hiding a giant from us. When you look up at the night sky, the bright band of the Milky Way stretches across it like a river of light. That band is gorgeous, and it is also a problem. It is so crowded with our galaxy's own stars, gas, and dust that it blocks the view of whatever lies behind it. Astronomers call this blocked off strip the zone of avoidance, because telescopes have long had to avoid it. A whole slice of the universe sits hidden back there, screened by the glare of our own galaxy. In 2020, a team of scientists found a way to peek behind the curtain. Rather than trying to see the hidden galaxies directly, they tracked how nearby galaxies move, how they get tugged and pulled by the gravity of whatever lurks beyond the bright band. From those motions, they reconstructed the shape of the thing doing the pulling. A hidden structure revealed by its gravity, like spotting an invisible whale by the swirl it leaves on the surface of the sea. What they uncovered is called the South Pole Wall. It is an immense curtain of thousands of galaxies, arcing across the southern sky, stretching nearly 1.5 billion light years from end to end. It had been sitting there the whole time, one of the largest structures in our own cosmic backyard, hidden simply because it lay behind the brightest part of our galaxy. Sit with that for a moment. This wall is relatively close to us, in cosmic terms, one of our nearest giant neighbors, and we missed it for the entire history of astronomy, because our own Milky Way stood in the way. It makes you wonder how many more giants are out there, screened by glare, waiting behind curtains of light we have not yet learned to see through. The South Pole Wall matters for the same reason the rings and arcs do. It is enormous, brushing right up against the size limit, another structure that strains the promise of a smooth and even universe. Each giant like this adds weight to a growing suspicion. The largest scales of the cosmos may be far lumpier, far more structured than the rule allows. And here is the unsettling pattern. The more carefully we look, and the cleverer our methods become, the more of these giants we find. They keep turning up, wall after wall, ring after ring, far too often to be rare freaks. They appear as if the universe is studded with them, and we are only now building eyes sharp enough to notice. The South Pole Wall, for all its size, still sits near the edge of what the rules can stretch to allow. It bends the smoothness rule hard. It does not quite shatter it. There is one structure, though, that leaves every other giant far behind. A thing so vast that it makes the South Pole Wall, the Big Ring, and the giant arc all look small. A structure so large that, when scientists first measured it, many refused to believe it could be real. It stretches across 1/10 of the entire observable universe, The largest known structure in the universe stretches across 10 billion light-years. It carries a grand name, the Hercules Corona Borealis Great Wall, after the constellations it sprawls behind. It is a colossal concentration of galaxies, the biggest single thing humans have ever mapped, and its size is almost impossible to take in. The observable universe, the entire bubble of space we can see, measures about 93 billion light-years across. This one structure spans roughly a tenth of that. A single formation, reaching across a tenth of everything we can observe. Scientists found it in a clever way, using some of the brightest explosions in existence. When certain massive stars die, or when dense dead stars collide, they release a flash of energy called a gamma-ray burst, briefly outshining entire galaxies. These bursts are so bright that we can see them from staggering distances, which makes them useful markers. Where you find a crowd of gamma-ray bursts clustered together, you find a crowd of galaxies, since the bursts come from dying stars inside them. Map the bursts, and you map the matter. When astronomers plotted these distant flashes, a vast clump appeared in one region of the sky. Far more bursts crowded together than random scatter could explain. That clump traced out the Great Wall, a sprawling region packed with galaxies on a scale that dwarfs everything else we have found. Try to picture the comparison. This Great Wall stretches nearly 8 times wider than the Big Ring, and the Big Ring already smashed through the size limit. The Great Wall blows past that limit by a margin that should be flatly, totally impossible. By the rules of a smooth universe, a structure this large should not exist anywhere, ever, in all the space we can see. That is exactly why some scientists are cautious about it. A structure this absurdly large strains belief so hard that researchers have questioned whether it is truly a single connected object, or whether the gamma-ray bursts only seem to cluster because of how they were counted. The Great Wall sits in honest dispute. Some studies defend it as real. Others argue it may be partly a trick of patchy data. The jury is still out, and that uncertainty is part of the story. Yet the bursts really do cluster, far more than chance should allow, and that clustering alone is hard to wave away. Whether the Great Wall is one solid structure or a loosely linked region, something out there has gathered an extraordinary amount of matter into one corner of the deep universe on a scale the smoothness rule swears is forbidden. And the Great Wall does not stand alone. The Big Ring, the Giant Arc, the Sloan Great Wall, the South Pole Wall. One by one, these giants have piled up, each one straining or breaking the size limit, each one whispering the same thing. The universe is far more structured at its largest scales than our deepest rule allows. So if the smoothness rule really is cracking, scientists need a reason, some new piece of physics, some hidden ingredient, some force capable of carving giant rings and walls into the fabric of space. And the explanations they have started to reach for are stranger than the structures themselves. The first one sounds like science fiction, cracks in space, left over from the birth of the universe. When the universe was born, it may have cracked. To picture how, think about water freezing into ice. As water turns solid, it freezes unevenly. Cracks and flaws appear, lines of stress frozen into the ice where different patches solidified out of step with each other. Some scientists believe the early universe did something similar. As the newborn cosmos cooled in its first fraction of a second, it may have set in place too quickly to stay perfectly smooth, leaving behind flaws frozen into the fabric of space itself. The most dramatic of these flaws would be long, thin lines called cosmic strings. A cosmic string would be a thread of pure, trapped energy, far thinner than an atom, yet stretching across unimaginable distances. And it would be staggeringly heavy. A short length of cosmic string could outweigh an entire mountain, and a longer stretch could rival a whole planet. These would be among the densest objects ever to exist, threads of leftover energy left hanging in space from the first instant of time. Here is why they matter for our mystery. A cosmic string is so massive that its gravity would warp everything around it. As a string moved through the early universe, it could have herded gas and matter along its path, sweeping galaxies into lines and loops, carving order into the cosmos on enormous scales. A string that whipped into a loop could, in theory, gather matter into a ring. A string under tension could draw matter into a long, sweeping arc. You can see where this is going. A ring, an arc, the exact shapes Lopez found, hanging side by side in the deep sky. Some scientists have wondered aloud whether cosmic strings could be the hidden hand behind these giants. Ancient threads from the birth of the universe, sculpting galaxies into shapes that gravity alone could never make in the time available. It is a thrilling idea, and an honest one to raise, because cosmic strings could sidestep the time problem entirely. They would have been born in the first instant, already vast, already stretching across what would become huge regions of space. A structure carved by one of these primordial threads would carry the fingerprint of the universe's very first moment, with no need to slowly assemble over billions of years. There is one catch, and it is a big one. No one has ever found a cosmic string. They remain a possibility, written in equations, predicted by some theories of the early universe and absent from others. Scientists have searched for their telltale signatures and come up empty so far. Cosmic strings might lace the entire universe, or they might never have existed at all. We genuinely do not know, so this explanation sits in a strange place. It would beautifully account for the rings and arcs, tying them to the deepest origins of the cosmos. It also rests on an object that has never once been seen. The idea is powerful and unproven at the same time, a maybe written across the sky. If cosmic strings are the answer, then the Big Ring is a scar from the birth of our universe. But there is another idea, stranger still, that pushes the scar even further back in time, past the birth of our universe entirely, to a universe that came before ours. What if our universe is not the first? That is the wild proposal of one of the most respected minds in physics, a scientist who won the Nobel Prize for his work on the deepest questions of the cosmos. His idea carries a long name, and the heart of it is simple and staggering. The Big Bang may have been a doorway rather than a true beginning, a handoff from a universe that existed before ours. In this picture, the universe goes through endless cycles. Each cycle begins with a bang and ends in the far, far future, when the cosmos has expanded into cold, empty darkness. Every star burned out, every black hole evaporated away. At that distant ending, the idea claims the universe somehow resets, and a fresh bang begins the next cycle. Bang, expansion, fade, reset. Over and over, forever, with no first cycle and no last. The most haunting part is what carries over. According to this theory, faint marks from the previous cycle can survive the reset and bleed through into the next one. Echoes, scars, patterns stamped into the new universe by enormous events in the old one, like the impression of a coin left behind in soft wax after the coin is gone. The biggest events in a dying universe would be the collisions of giant black holes, monsters swallowing each other in the final darkness. Each collision would send a ripple outward, and that ripple, the theory suggests, could survive into the next cycle as a ring-shaped mark in the sky, a circle printed onto our universe by a catastrophe in the one before. You can feel why this idea brushes up against our mystery. A ring printed into the sky from a previous universe would owe nothing to our size limit, or our clock, or our slow gravity. It would be a fossil from another age entirely, stamped in at the very start of ours. The Big Ring, in this view, could be a message in a bottle from a cosmos that died before the sun, the earth, or the first star had any chance to exist. It is a breathtaking thought, and a deeply controversial one. Most scientists are skeptical. The idea is hard to test. The supposed echoes are faint and fiercely debated, and extraordinary claims like this demand mountains of proof that simply are not in yet. Many researchers think the patterns pointed to as evidence are just random noise dressed up as meaning. This idea lives far out on the edge of accepted science, brilliant and unproven, defended by a few and doubted by many. Still, it captures something important about where this mystery has pushed us. The giant structures are so hard to explain that serious scientists are willing to reach for serious strangeness, from threads left by the birth of the universe to scars from a universe that came before. When the ordinary explanations fail, the extraordinary ones get their hearing. And while these grand theories battle over the rings and arcs, a separate set of cracks has been spreading through cosmology, quietly, in the background. The giant structures are one sign among several that something is wrong with our picture of the universe. The next sign shows up in the oldest light in existence. The oldest light in the universe should be perfectly even. The maps tell a different story. Spread across the entire sky is a faint glow left over from the Big Bang itself, the cooled afterglow of the universe's hot beginning. It comes at us from every direction, a gentle hum of ancient light that has traveled almost the whole age of the cosmos to reach us. This afterglow is the closest thing we have to a baby photo of the universe, a snapshot from when it was only a few 100,000 years old. According to the smoothness rule, this glow should look the same in every direction. The tiny ripples in it, the faint warm spots and cool spots, should be sprinkled randomly across the sky, with no pattern, no alignment, no direction picked out. A universe with no favored direction should leave its baby photo evenly speckled, like static on an old television. When scientists mapped the glow in fine detail, they found something that should not be there. Some of the largest ripples seem to line up. They point along a common direction, as if the early universe had an axis, a preferred way of facing, running through it. Researchers gave this strange alignment a dramatic nickname. They called it the axis of evil, because it quietly threatens one of the two great promises of cosmology, the promise that no direction in space is special. Picture rolling thousands of dice across a table and finding that a surprising number of them landed pointing the same way. One or two lining up is chance. A whole crowd of them aligned makes you suspect the table is tilted, that some hidden force nudged them all in one direction. The aligned ripples in the ancient glow give scientists that same uneasy feeling. Something may be tilting the table of the entire universe. Now place this next to the giant rings and walls. The structures suggest the universe is too lumpy at the largest scales. The aligned glow suggests the universe has a direction it is not supposed to have. Both point at the same crack from different angles. Both whisper that the cosmos may be less smooth and even and democratic than the cosmological principle insists. Scientists are careful here, and rightly so. The alignment in the ancient glow might be a fluke, a rare roll of the dice that looks meaningful by accident. It might come from some error in how we filter our own galaxy's light out of the map. Many researchers suspect it will eventually fade into coincidence once we understand it better. The axis of evil is a genuine puzzle, still argued over, far from settled. Yet it refuses to fully go away. Survey after survey, the alignment keeps showing up, stubborn and strange, in the most carefully measured light in all of science. And it is one of several hints that our tidy picture of the cosmos has loose threads that keep getting pulled. The next loose thread may be the most serious of all. It comes down to a single number, the most important number in cosmology, and the fact that we have measured it two different ways and gotten two different answers. The universe, it seems, cannot agree with itself on how fast it is growing. The universe is expanding, and scientists cannot agree on how fast. This should be a settled number. The expansion rate is one of the most basic facts about the cosmos, the speed at which space itself is stretching and carrying galaxies apart. Scientists have two trusted ways to measure it, and for years they assumed both methods would land on the same answer. Instead, the two answers stubbornly disagree, and the gap between them will not close. The first method looks at the ancient afterglow of the Big Bang, that same baby photo of the early universe. By studying the ripples in it, scientists can calculate how fast the universe should be expanding today. This is the early universe's own prediction, read straight from its infancy. The second method looks at the nearby, present-day universe. Scientists measure the real distances to galaxies and watch how fast they are racing away, timing the expansion directly, here and now. This is the grown-up universe, measured in person. The two answers should match. They do not. The present-day universe appears to be expanding faster than the early universe says it should. The disagreement is small in raw numbers and rock solid, showing up again and again no matter how carefully scientists check their work. They gave this stubborn mismatch a name, the Hubble tension, after the astronomer who first proved the universe was expanding at all. Imagine two reliable clocks, one set in the morning and one checked at night, that keep drifting apart no matter how often you reset them. At first, you blame a mistake, but when every clock, every method, every careful recheck keeps showing the same drift, you stop blaming the clocks. You start to suspect that time itself is doing something you do not understand. That is roughly where cosmologists stand with the expansion of the universe. The tension has grown into one of the deepest problems in modern science. For a while, scientists hoped it was a measuring error, a mistake hiding in one of the two methods. But the measurements keep getting sharper, the error bars keep shrinking, and the gap holds firm. More and more researchers now suspect the mismatch is real, and that it points to something genuinely missing from our understanding of the universe. And here is why it belongs in this story. The Hubble tension, the aligned ancient light, and the giant impossible structures may all be separate symptoms of one underlying illness. Each one, on its own, might be explained away. Together, they form a pattern, our standard model of the cosmos. The proud theory that has passed so many tests keeps stumbling in exactly the places where we push it hardest. When a single theory starts failing in several different ways at once, scientists begin to wonder if the problem lies deeper than any one measurement. Maybe the issue hides somewhere other than our telescopes or our methods. Maybe it lives in the recipe itself, in our list of what the universe is actually made of. And that recipe hides an embarrassing secret. Almost everything in the universe is made of stuff we have never identified, never seen, and cannot explain. Here is a fact that should be more famous than it is. Everything you have ever seen, touched, or known is made of a tiny sliver of the universe. Add up all the ordinary matter in the cosmos, every star, every planet, every galaxy, every atom in your body, and it comes to only about 5% of what the universe contains. The other 95% is made of two things we cannot see and barely understand. The first is dark matter, the invisible material we met earlier, the unseen frame that galaxies are built on. It makes up around a quarter of the universe. We know it is there only because of its gravity, the way it pulls on the things we can see. No one has ever caught a single particle of it. It passes through walls, through planets, through you, leaving no trace but its weight. The second is even stranger, and it makes up the largest share of all, roughly 2/3 of everything. Scientists call it dark energy, and it is the name we give to a mysterious push driving the universe to expand faster and faster over time. Something is pressing space apart, speeding up the growth of the cosmos, and we do not know what it is. We named it, and naming a thing is a long way from understanding it. So step back and look at our recipe for the universe. A small dash of ordinary matter, the only part we truly know. A large helping of invisible dark matter, sensed only by its pull, and a giant pour of dark energy, a force we cannot explain at all. Nearly the entire universe is made of question marks. We have been writing confident equations about a cosmos whose main ingredients are mysteries. Now, you can see how a wrong recipe might explain everything. If we have misjudged dark matter, then our predictions for how structures form could be off, and giant rings and walls might be easier to build than we thought. If we have misjudged dark energy, then our measurements of the universe's expansion could drift, and the Hubble tension could be the result. The strange structures and the strange numbers might all trace back to the same source, the dark ingredients we do not understand. And recently, a giant new survey delivered a jolt. By mapping millions of galaxies across the sky to study how the universe has expanded, scientists found early hints that dark energy may have been changing all along. It may have pushed harder in the past and gentler now, slowly shifting over the life of the cosmos. If that holds up, it would overturn a core assumption built into our standard model, a change so big that one scientist called it a major shift in how we see the universe. The findings are still fresh, still being checked, still uncertain. Extraordinary claims need time and repetition before anyone can be sure. But the direction is clear, and it echoes everything else in this story. The cracks keep widening, the standard model keeps wobbling, the universe keeps refusing to behave the way our textbooks promised, all of which leads to a single, dizzying possibility. The boldest idea of all. Maybe the smoothness rule was simply wrong from the start, and the universe has structure stretching up and up, with no ceiling at all. What if the universe never smooths out at all? Every rule in this story has leaned on one assumption, that somewhere, at some grand size, the lumps stop and the smoothness begins. Galaxies cluster into groups, groups into walls, walls into the cosmic web, and then, the rule promises, the pattern finally dissolves into an even haze. The smoothness has to start somewhere. That has always been the bet. The giant rings and arcs and walls poke at a frightening alternative. What if the lumps never stop? What if you could zoom out past the cosmic web, past the giant walls, past the big ring, and keep finding bigger structures at every scale, forever, with no ceiling, no point where the universe finally settles into smoothness? Scientists have a word for a pattern that repeats at every scale. They call it a fractal. Picture the branching of a tree. A great limb splits into smaller branches. Each branch splits into twigs, each twig into tiny shoots, and the same branching shape shows up no matter how closely you look. A coastline works the same way. A whole shoreline is jagged, and each bay holds smaller jagged inlets, and each inlet holds smaller jagged notches. The same roughness at every zoom. A fractal universe would look like that. Structure inside structure inside structure, all the way up, with no largest size and no smooth scale anywhere. The giant walls would fit right in, exactly what you would expect from a universe that is lumpy at every level you care to measure. This idea would tear the foundations out from under modern cosmology. Almost every calculation about the age, size, and fate of the universe assumes the smoothness kicks in. Take that away, and those clean equations lose their footing. The math that has guided us for a century would need rebuilding from the ground up. It is the kind of shift that comes along once in a generation, if that. Most scientists are not ready to go this far, and for good reason. The evidence still mostly favors a universe that does smooth out, eventually, at the largest scales. The deepest surveys, including the great map made by the James Webb Space Telescope, still show a cosmos that looks fairly even when you zoom out far enough. The giant structures are real and troubling, and they may still be rare outliers rather than proof of endless lumpiness. So this stands as the boldest reading of the mystery, the one that would change the most if it turned out to be true. It hangs out at the far edge of possibility, waiting for evidence to either lift it up or knock it down. For now, it is a question mark drawn at the very top of the cosmic ladder. We do not know how high the structures go. We have not yet found the ceiling, if there even is one. And the only way to settle it is to look, to map more of the sky, deeper and wider than ever, until we either find the smoothness the rule promises, or prove that it was never there. That hunt is already underway. Right now, new machines are scanning the heavens, building maps so vast they will dwarf everything we have charted before, and what they find in the next few years may finally tell us which universe we live in. Right now, machines are racing to map the universe as never before. In the mountains of Arizona, a single telescope has been fitted with thousands of tiny robotic eyes, each one able to lock onto a separate galaxy and measure its distance. Every night, it captures the light of tens of thousands of galaxies at once, building a three-dimensional map of the cosmos on a scale that would have seemed like fantasy a generation ago. Its goal is to chart millions upon millions of galaxies, laying out the cosmic web in enough detail to test the smoothness rule head-on. Out in space, a new telescope launched by Europe has begun its own enormous survey, designed to map the shapes and positions of billions of galaxies across a huge swath of the sky. By measuring how the light of distant galaxies gets bent and stretched, it can trace the hidden dark matter between them, drawing the invisible scaffolding of the universe in sharper focus than ever before. Another powerful observatory is being prepared to join the hunt, built to survey vast regions of sky with stunning depth. And the James Webb Space Telescope keeps working, returning again and again to the deep, ancient universe, sharpening our view of the first galaxies and the early cosmic web. The same telescope that helped open this mystery is helping to chase it down. Put these machines together, and the next several years could become the greatest mapping effort in the history of astronomy. For the first time, scientists will have charts detailed enough to settle the question that runs through this entire story. Does the universe truly smooth out at the largest scales, exactly as the rule promises? Or do the giant structures keep appearing, bigger and stranger, until the rule finally breaks for good? The answer will arrive slowly, as the maps fill in, galaxy by galaxy, region by region. Scientists will count the giants. They will measure how the structures are spread across the sky. They will check whether there is a special direction, a ceiling on size, a point where the lumps finally fade. Piece by piece, the new maps will either rescue the smooth universe or bury it. Whatever they find, the stakes reach far beyond a single rule. If the smoothness holds, our standard model survives a brutal test, and we can trust our deepest map of reality a little more. If the smoothness fails, then almost everything resting on it comes up for question. The age of the universe, its true size, its hidden ingredients, its final fate. We would be living in a stranger cosmos than we ever imagined, and we would have to learn it almost from scratch. That is the strange gift of the Big Ring and the giants beside it. They have taken our proudest, most tested story of the universe and exposed a crack in its foundation. They have forced some of the smartest people alive to ask whether the rules we trusted were ever really rules at all. We are standing at a rare moment in science, the moment just before a long-held belief either proves itself or falls. The telescopes are watching, the maps are filling in, and the universe is about to tell us whether it has been keeping its deepest promise or quietly breaking it the whole time. Step back and look at how far we have come. We started with a simple promise, the idea that the universe is smooth and even on the grandest scales, the same in every direction, the same from every place. It was the floor beneath all of cosmology, so trusted that almost no one thought to question it. Then a telescope colder than the dark, parked a million miles from Earth, began sending back the deep sky in detail no one had ever seen. It found galaxies too big for their age, grown giants standing in a universe still in its infancy. It helped map the cosmic web back toward the dawn of time, and in the shadows cast by distant quasars, scientists traced shapes that should not exist: a sweeping arc, a coiled ring posing as a circle, walls of galaxies stretching across a tenth of all we can see. Every one of these giants leans on the same crack. Each one is too large, too ordered, too quickly made for a universe that was supposed to grow smooth, and they do not stand alone. The oldest light in the sky seems to point a direction it should not have. The expansion of the universe gives two answers that refuse to agree. Nearly everything in the cosmos turns out to be made of dark ingredients we have named but never understood. Each crack might be explained on its own. Together, they run through the whole house. What does it mean for you? It means you are alive at a rare moment, the moment when a great scientific story is being tested to its limits. For 100 years, we believed we had the basic shape of the universe figured out. The rings and walls and tensions are quietly asking whether we had it right at all. You are watching, in real time, as the foundations of our picture of reality get pushed and prodded and maybe rebuilt. And there is something humbling in it, something almost beautiful. We are small. We sit on one ordinary planet, circling one ordinary star, near the edge of one ordinary galaxy, which itself hangs on a single thread of the cosmic web. From that tiny perch, with telescopes and patience and stubborn curiosity, we have managed to spot structures billions of light years across and ask whether the universe is keeping its oldest promise. That a creature this small can even pose the question is a kind of wonder all its own. The honest truth is that we do not yet know the answer. The giants might turn out to be rare flukes, and the smooth universe might survive its hardest test. Or the structures might keep growing, the cracks might keep spreading, and we might learn that the cosmos is stranger, lumpier, and more surprising than anyone dared to think. Both futures are still open. The data is still coming in. What is certain is this. Somewhere out in the deep dark, a ring of galaxies 1.3 billion light-years across is hanging in the sky, coiled like a spring, breaking a rule the universe was supposed to obey. It has been there for billions of years, waiting, and only now, with the right eyes and the right questions, have we finally begun to see it. The universe has been keeping secrets on a scale we are only starting to imagine, and the search for the next one has already begun.